Introduction to Capacitive Sensing, Part 1, Capacitive Sensing and the Programmable System on Chip family. Welcome to the Introduction to Capacitive Sensing training module. This module will cover what capacitive sensing is, how it works, and where it can be applied. At the end of this course, you will be able to list the advantages of using capacitive touch-based systems over mechanical buttons and sliders, and also describe how capacitive sensing distinguishes the presence or absence of a conductive element. We will also introduce Cypress's Programmable System on Chip family. Capacitive sensing is making its way into more and more uses every day, from mobile handsets to computers to point-of-service terminals and home electronics. Capacitive sensing is showing up in applications everywhere. But what exactly is capacitive sensing? It is an alternative to traditional mechanical buttons and sliders in electronics. Instead of sensing the physical state of a button, it detects the presence or absence of a conductive object. Most simply, that object is a part of the human body, like a finger. There are actually several different reasons to implement a touch-based system. One of the most basic reasons to implement a touch-based solution is for higher reliability and durability. Buttons in a public kiosk are subject to a lot of abuse and traffic. Mechanical buttons can wear very easily and cause many failures. Having to replace buttons and fix mechanical sensors can easily increase total system costs. Using a touch-based solution is more durable and reduces total costs in the long run. Touch-based systems also allow more flexibility, as the buttons can be multi-use. For example, on a traditional home telephone, the mechanical button for the number 1 can really only serve to dial the number 1 or possibly represent a menu option when specified. With touch-based buttons, there are several ways to design the interface. This is only limited by the needs of the design. In the same sense as a single button can serve many purposes, a touch-based system allows more usage in a limited amount of space. Finally, one of the key advantages of using touch-based systems over mechanical buttons is that it can improve the end-user experience. Touch-based solutions are oftentimes more intuitive and user-friendly. These reasons all contribute to the growing adoption of touch-based solutions. Strategy Analytics believes that by 2012, as many as 40% of cell phones could be using touch-sensitive technology, compared with only 3% today. There are several different ways to implement a touch-based system. This includes the use of resistive film, infrared sensors, or even surface acoustic waves. So with the different options available, why use capacitive sensing? First, there is sensitivity. Capacitive sensing is enabled with a light touch of a finger, without the need for a stylus or pressure that is sometimes required with resistive films. Second, there is durability. As previously mentioned, touch-based solutions are more durable than mechanical buttons and switches. However, among the touch-based solutions, capacitive sensors are extremely durable, whereas the infrared solution can be adversely affected by surface contaminants. Capacitive sensing is environment resistant. Finally, there is flexibility. Because capacitive sensing can be used with a wide range of overlay materials with varying degrees of resolution and accuracy, it is not limited to certain applications. Capacitive sensing can be used in consumer electronics like mobile handsets, MP3 players, digital cameras, and it can also be used in industrial or home appliances like washing machines or kiosks. So how does capacitive sensing work? To understand how a capacitive sensor works, here is a cross-section of a single capacitive sensing button. Under some overlay material, in this case glass, there are conductive copper areas and conductive sensors. Whenever two conductive elements are within close proximity to each other, a capacitance is created, noted as C sub P in this diagram, which is generated by coupling the sensor pad and ground plane. C sub P is the parasitic capacitance and is typically on the order of 10 picofarads to 300 picofarads. Now the proximity of the sensor and ground planes also create a fringe electric field that passes through the overlay. The tissue of the human body is basically a conductor as well. Placing a finger near fringing electric fields adds conductive surface area to the capacitive system. This additional finger capacitance, noted here as C sub F, is, however, on the order of 0.1 picofarads to 10 picofarads. So although the presence of a finger induces change, the scale of the change in comparison to the parasitic capacitance is quite small. The sensor's measured capacitance is called C sub x. With no finger present, C sub x is basically equal to C sub p. When a finger is present, then, C sub x is a combination of C sub p and C sub f. PSoC stands for Programmable System on Chip. PSoC is a device that has an array of hardware blocks that can be configured to perform a variety of functions. The analog blocks can be configured as analog to digital converters, digital to analog converters, filters, and even capacitive sensors. We'll discuss implementation of capacitive sensors a little later. The digital blocks can be configured as digital functions such as counters, pulse width modulators, and communication interfaces like UART and SPI. I2C communication is included on PSoCs without the use of the digital resources. In any embedded system, one would expect there to be memory. PSoCs have anywhere from 4K to 32K of flash memory, depending on the device family. SRAM is also available in different sizes, from 256 bytes to 2 kilobytes. The onboard microcontroller is the same microcontroller that is used in Cypress's USB products. Shown here is a block diagram of a PSoC device. On the left side of the diagram are the standard microcontroller elements such as oscillators, charge pumps, memory, and the controller itself. On the right side of the diagram is what gives PSoC its real power. These digital and analog blocks can be configured as functions such as a 16-bit pulse width modulator, a filter, an analog to digital converter, or a full or half duplex UART. These blocks can be reconfigured in runtime to have different functionality, such as that of timers, amplifiers, or comparators. The microcontroller and the digital and analog blocks are routed to I/O using programmable interconnects, providing even more flexibility. This flexibility in I/O connections is particularly useful in capacitive sensing applications, where reduction in parasitic capacitance and optimization of signals is so valuable. All of this flexibility and configurability manifests itself as a highly flexible design platform, allowing for more rapid design changes and easy migration to new projects. This reduces development time and simplifies manufacturing. The integration capabilities of PSoC reduce the component count as shown in the figure here. The figure on the top is before PSoC and has considerably more parts, ICs and passives, than the board on the bottom. All of the configurability and flexibility is translated to capacitive sensing with PSoC. The configurable analog and digital blocks, as well as the interconnects, are used to create all forms of capacitive inputs, buttons, sliders, touchpads, touchscreens, and proximity sensors with the same devices and at the same time if necessary. Furthermore, PSoC can function as a CapSense device only or as part of a larger system with CapSense Plus. The same features that are used for capacitive sensing can be used to drive motors, LEDs, speakers, measure voltages, and communicate to the host. CapSense can also be used as a touchscreen controller. This allows a whole new world of applications beyond buttons and sliders. PSoC has three main families of CapSense-enabled products. The smallest devices are offered in 3x3 QFN packages. Larger devices include an 8x8 QFN as well as SSOP and SOIC footprints. I/O ranges from 13 in the smaller devices to 48 in the larger devices. Low sleep current in all of the devices allows users to reduce the average current consumption for CapSense design significantly. CapSense Plus is enabled in all parts, but has considerably more functionality, especially with dynamic reconfiguration in the larger devices. There are also several development kits available to help begin your CapSense design. Specifically, there are three kits available today. The CY3203A CapSense kit utilizes the CY8C 20X34 device family, while the CY3213A CapSense kit utilizes the CY8C 21X34 device family. Finally, there is the CY3214 PSoC Eval USB development kit that features the CY8C 24X94 device family. Each of these development kits comes complete with the software and hardware necessary to begin development with CapSense, as well as detailed example projects that can be easily modified to your needs. Once you have developed your project, the kit also allows you to connect directly to PSoC's in-circuit emulator to debug and test the final project. Cypress has a suite of design tools, starting with the free integrated development environment, PSoC Designer. PSoC Designer allows engineers to define the system parameters and select, place, and configure predefined analog and digital functions using the device editor. CapSense functions are included in the library of functions. The screenshot on the right of this screen shows the device editor for CSA PSoC Designer, allowing engineers to write application code with the application editor and step through the program with the debugger. Cypress offers a low-cost, in-circuit emulator as well as a comprehensive library of application notes and technical articles. The emulator consists of a base unit that connects to the PC by way of the parallel or USB port. The base unit is universal and will operate with all PSoC devices. Using the integrated development environment, CapSense designers are able to select and place their CapSense user module. A wizard allows definition of buttons and sliders and pin assignment. Pins are assigned by dragging available pins over the capacitive inputs. User module sensitivity and high-level functions are defined in user module parameters and API calls.